Welcome to CVMP, the 17th ACM SIGGRAPH European Conference on Visual Media Production. My name is Richardt from the University of Bath, and it's my great pleasure to welcome you all to this virtual edition of CVMP. Over the years, CVMP has built a reputation as the prime venue for researchers to meet with practitioners in the creative industries. CVMP brings together production and post-production specialists from the world of film, broadcast, games, immersive, with imaging and graphics researchers. It brings together expertise in video processing, computer vision, machine learning, computer graphics, animation, and physical simulation. This year has been challenging for many of us, both professionally and personally. 2020 has brought sweeping changes to our way of living and our way of working. One of the changes we had to make as conference organizers was to move CVMP online. In doing so, we were determined to make the most of the unique opportunities this offered in terms of attracting a broader audience and a more diverse set of speakers than ever before. Okay, I would like to start with some statistics. So as of this morning, we have a record total of 240 attendees from 36 countries on 5 different continents. And I dare to say that this is the most diverse and broad attendance at CVMP ever before. We will have 8 hours of networking sessions planned throughout today and tomorrow. There's 7 short papers and 1 live demo. We have 6 themed networking sessions that are taking place over the networking lunch sessions. We have 5 full paper presentations, 4 exciting keynotes, and 4 industry presentations, 2 full days of technical content and networking opportunities, 1 special session on virtual production, and 0 registration fee, which we're particularly proud of this year. So, how does CVMP work this year? We will have 3 different pillars on which the virtual conference is built. The first pillar is our conference website. You can find the conference program there, and it links to the other 2 pillars. We will be streaming sessions, papers, presentations live and pre-recorded to YouTube. So these will be streamed live. So you can follow them along live in UK time, or you can catch up on them later as well. So most sessions will be archived also for posterity on YouTube. The third pillar is Discord, which we are using for discussions and networking. We have tested the setup a few times before, but it is still new to us as well. So if something goes wrong or we have technical difficulties, I would kindly ask you to please be patient, and we'll be back with you as soon as we can. So let's take a more detailed look at these 3 pillars. If you're following along on Twitter, please use the hashtag CVMP2020. And we start with our conference website. So the program you can see there lists all the sessions that we have planned out for you. We have linked them to the other 2 pillars, so you can follow along the sessions on YouTube there for the technical part of the program, or you can connect on Discord for the discussion and networking components. And if you follow this link at the top here for the YouTube video stream, you get to YouTube, where you can find a playlist of all the sessions that we have scheduled for you for CVMP 2020. On Discord, some of you might be familiar with Discord, but to others it will probably look familiar as well as a chat application. You can see who is online, you can see the different channels that we have prepared for you, the messaging area in the middle, where you can type your messages and contribute to the chat, and use some emoticons as well to spice it up. Discord supports 2 different types of channels. So there's text channels that are indicated with the hash icon, where you can just chat normally, and there's also audio channels where you can join with audio and video, and we will use those mostly for networking sessions, so to have a more personal touch, so you don't have to type everything. So we have here highlighted the first time attendees channel that we are encouraging everybody who is new to CVMP to join. We had already a bit of discussion going on this morning, and we have another session going on tomorrow morning at 9 AM there as well. We have a few other channels. We have a help desk channel, so if you have any issues or problems, please reach out there and somebody will be with you to help you. We have a suggestion channel if you have any ideas how to improve the CVMP experience, and we will try to act on your suggestions as quickly as we can throughout the conference. To use Discord, you can use the invitation link that we sent out after you registered for CVMP. The use of Discord is only limited to registered attendees. So you can still register along today and tomorrow if you're watching this live. And you can use Discord completely in your browser, so you don't have to install anything. And some browsers such as Chrome will also support video calls for our networking sessions. Okay, let's have a quick overview rundown of our program. So CVMP takes place today and tomorrow from 9 a.m. to 5 p.m. approximately. So we start in the mornings with a morning coffee networking session. So join us there to say hi to your colleagues and friends that you haven't seen in a while, or make new friends and talk to people who might be interested in topics that you're working on or interested in. Then at 10 a.m. UK time, and all times are in Greenwich Mean Time or UK time, we are right now in the welcome session, but after that, this will be followed by the first papers session, and tomorrow will be the second paper session. Then at 11, we have the morning keynote, today by Sarah Tico, who will be talking about her work on immersive art and healthcare. And tomorrow's keynote is by Ben Radcliffe from Unity, who will be talking about the road to real time. Then at 12, we have a networking lunch session. So bring your lunch and join the networking sessions in Discord to have a chat with people. At 1 p.m., we have planned themed networking sessions. So we have planned 6 networking sessions in total, 3 today and 3 tomorrow. So today's sessions are on AR, MR, VR, and XR, chaired by or led by Stuart James from the IIT in Genova. Interactive media, led by Nigel Williams from Unity. And scene capture, led by Alyosha Smolic from Trinity College Dublin. Tomorrow's sessions are on computational photography, led by Rafael Mantiok at Cambridge, digital humans, led by Darren Koska from Bath, and production tools, led by Neil Campbell at Bath. Then at 2 p.m. we are back with a technical program. Today we have an industry talk by Intel Studios. We have 6 short paper presentations and 1 live demo. And tomorrow we have a special session on virtual production. So this is a focus of this year's CVMP, virtual production. And we have 3 exciting industry talks for you by Dimension Studios, by Has Films, and by NVIDIA. At 3 p.m., we then have a coffee Q&A session and networking session. So today's coffee and networking session is also a Q&A session for the short papers and the demos. So the authors will be there to answer questions that you might have. And tomorrow's coffee and networking session will also double as a Q&A session on the virtual production special session. Then at 4 p.m., we have an afternoon keynote. Today's keynote speaker in the afternoon is Paul de Berwijk from Google Research. We'll be talking about light fields, light stages, and the future of virtual production. And tomorrow's afternoon keynote is by Anju Kanazawa from UC Berkeley. We're talking about perceiving humans, animals, and objects in the 3D world. Following at 5 p.m. today, there's a networking reception that is kindly hosted by the Center for Digital Entertainment at the University of Bath. This is taking place in Gathertown, and we will be sending out joining instructions in the afternoon coffee break via Discord, so you can follow along there. Bring along your favorite drink and have a chat with people and explore the space, talk to some students, talk to some colleagues. This will be free for all attendees to join as well. And tomorrow we'll be closing with the announcement of prizes and other announcements. So this really exciting program would not be possible to put together alone. So I've been joined by a very capable and hands-on team. Patrick Huber from the University of York is a full papers chair for this year. Marco Volino is a short papers and demo chair. Marco is from the University of Surrey. Nigel Williams is the industry chair. He's working at Unity Technologies. Melissa Green is our conference secretary at the University of York. And Armin Mustafa is a public relations chair at the University of Surrey. In addition, we have a range of helpers that you might see around at the conference. Joanna Tarko, also from Bath, is the streaming chair. So she is working hard behind the scenes to make sure all our videos end up on YouTube. We have Manuel Rey Arrea, our Discord chair. So he will be a friendly face on Discord. And we have Alex Rotsides and Ruben Lindros as Zoom hosts working behind the scenes. One thing that we are particularly proud of this year that CVMP is free to attend, and this would not be possible without our range of sponsors. So the conference itself is sponsored by ACM SIGGRAPH, who is also sponsoring the Best Paper Prize. Our gold sponsor is NVIDIA, who's kindly sponsoring the Best Short Paper Prize with an enterprise class GPU. We have silver sponsors YouTube and Adobe, who make it possible for people to attend for free from all over the world. And we have a range of bronze sponsors from Activision, 40Face, and some academic sponsors, the Center for Analysis of Motion, Entertainment Research and Applications, short camera, at the University of Bath, the Center for Digital Entertainment, also at the University of Bath, and the Center for Vision, Speech, and Signal Processing at the University of Surrey. And that, I would like to declare CVMP opened, it's my great pleasure now to hand over to Will Smith, who will be chairing the first paper session. Go ahead, Will.
Good morning, everyone, or good afternoon or evening, depending on where you are in the world. So it's a great pleasure to chair the first paper session at CVMP this year. And just before that starts, I just want to congratulate all the organisers, Christian and all the rest of the team that you mentioned, on pulling together a really amazing programme in very challenging circumstances. So the first paper session is on the topic of learning, and we've got two very interesting papers. I would encourage you, while you're watching along, to put your questions into the Discord chat, and then we'll have a Q&A session after the two videos have played. Okay, so let's hand over to the talks.
Welcome to my talk about neural phase models for example-based visual speech synthesis. My name is Wolfgang Paier, and I'm a researcher in the Computer Vision and Graphics group at Fraunhofer Heinrich Hertz Institute in Berlin. Volumetric video capture has become a popular technique in recent years to create high-quality 3D models of humans. On the left side and in the middle, you can see pictures of a typical volumetric capture studio that consists of many high-resolution cameras that are placed around the actor to give a 360-degree view. Based on this data, we, for example, create photorealistic 3D human models that can help us to develop new ways of movie or video productions like the one on the right side. But apart from that, we can of course also create animatable human models from the captured data. This video shows, for example, the rendering of a virtual sign language interpreter who presents a weather forecast in Swiss-German sign language. We animate this model with a skeleton-based approach, but since facial expressions are an essential part of sign language, we explore new techniques apart from classical blend shapes to create realistic animation of human faces. In this talk, I will focus on mouth animation according to certain input signals like, for example, text or visemes. This task is called visual speech synthesis. Our animation approach consists of two parts. First, we create a neural face model that provides a parametric representation of facial expressions. This gives us a joint representation of texture and geometry for our model. And it helps us to synthesize detailed facial expressions like the one you can see in the upper picture. Also, it helps to interpolate faithfully between facial expressions. And second, I present an example-based animation approach that uses this neural face model to combine samples of captured speech and synthesize also words that have not been captured. With this, we are able to synthesize a wide range of visual speech based on a comparable small set of data samples, which can be used to synthesize the mouthings for our virtual sign language interpreter. In order to train the neural face model, we need data. Therefore, we captured an actress in our volumetric video studio. We use 16 high-resolution stereo cameras. On the right side, you can see sample images of each captured viewpoint. To generate the training data, we use a simple geometry model with 15 blend shapes and track the rigid motion as well as expression in the multi-view video footage. After the tracking, we use the known head pose and face geometry to extract video textures from the captured footage. Video texture means that we don't use a single static texture for our face, but instead, we extract one texture for each recorded frame. This way, we can reproduce small motions and fine details that are difficult to represent with geometry alone. The result of this process are long sequences of geometry and texture, like you can see in this video. While the geometry model alone is not very detailed, a combination of dynamic texture and geometry yields a good representation of the captured performance. In the next slides, I will speak about the neural face model. The main purpose is to create parametric representation of the captured geometry and texture data. We encode texture as well as PCA weights for each captured video frame and store the corresponding expression vectors in a database. Our phase model is implemented as a variational autoencoder. The basic principle is rather simple. First, textures are fed into the convolutional texture encoder. The resulting texture code is combined with the geometry PCA weights and transformed to a latent feature vector. Since we have a variational autoencoder, we estimate the variance of the expression vector. This way, the autoencoder generates a smooth latent parameter space that allows sampling as well as plausible interpolation of facial expressions. Based on this latent expression vector, we also reconstruct the RGB texture and the PCA weights. In addition, we implemented a discriminator network, which distinguishes real textures from synthesized ones. It acts as a trainable loss function that improves the quality of the reconstructed face textures, because a pure variational autoencoder would produce blurry textures. After training, we use this network to compute a latent representation of all the captured face data. This slide shows a comparison of the reconstructed facial expressions with the original video on the right side. Even though we use a quite coarse geometry model, we can faithfully reproduce facial expressions in complex areas like the mouth cavity, which is not represented in geometry at all. Also, details like wrinkles and hair strands are still visible. Now I will explain the animation part. Using these neural face models, we transformed the captured speech data into sequences of latent feature vectors. This reduces the memory requirements and also helps generating smooth transitions between samples. We break the captured videos into short sequences, which represent vizims. On the right side, you can see our vizim dictionary. It consists of 13 vizims. The key concept of our approach is that we reuse these short motion samples and concatenate them to synthesize the animation parameters for new words that have not been captured. The challenge, however, is that a large number of possible combinations, because we have many samples that potentially fit for each vizim in a query. And out of all these possible combinations, we want to find the optimal solution. Optimal means that we correctly reproduce the visual speech and we do not introduce artifacts at transitions. As a side note, there is an effect called co-articulation. This means that during speech, successive sounds are articulated together. This makes our problem a bit more difficult, because the appearance of a vizim depends also on the surrounding vizims. The images on the bottom of the slide demonstrate this effect. You can see 4 instances of a T in the German words. But due to co-articulation, they look quite different. We take this effect into account by describing a sample not only by the vizim itself, but also by its surrounding vizims. So, for example, to represent the German word cult, which means cold, we use 4 vizims: the minus, the A, the L, and the T. In the extended representation, this becomes a hash minus A, minus AL, ALT, and LT hash. The hash simply means no vizim. This demonstrates also an advantage of our approach. Since we reuse the captured data of real people, we can easily reproduce effects like this. In order to find the best possible solution, we formulate this task as a discrete optimization problem that can be solved with graph cuts. Our objective consists of 2 terms: a data term U that makes sure that for each vizim we choose a sample that matches the vizim class, and a neighborhood term B that ensures the transitions between consecutive vizims are smooth. We achieve this by penalizing large deviations in an overlapping region of both vizims. Term B has another function as well. It helps finding a unique solution if the extended label of multiple candidate samples fits equally well, or if a certain variant of a vizim is in a database. To reduce the computation time, we only use a subset of samples from our database, because we can simply ignore all samples that are that are not relevant for the query. We solved the task with alpha expansion. It takes approximately between 24 and 600 milliseconds, depending on the length of the query sequence. However, our approach still can be used for real-time animation, because the duration of synthesized words is usually much longer than the computation time. After concatenating the selected Vizim samples, we create seamless transitions by performing gradient domain blending in latent space. On the last slides, I will show a few example animations where you can compare the synthesized words against the captured versions. They are not part of the animation database, otherwise our algorithm would exactly reproduce them. Here, for example, the synthesized German word Hochnebel, which means low stratus. This slide shows the German word Meteo, which means weather report. It's worth noting that the timing between the synthesized and the real version can differ slightly, but this usually does not degrade the comprehensibility. And on the last slide, you can see a synthesized version of the German word November. In general, we see that the synthesized versions are very close to the target words, but differ slightly in timing and expression. Today I presented an example-based approach for the animation of human faces. The key idea is to combine recent technologies like neural networks with classical approaches like example-based animation. This way we can solve problems that are typical for example-based approaches like artifacts due to interpolation of raw data and high memory requirements. We achieve this by using the neural face model that can synthesize plausible transitions, and instead of working with raw data, we only store latent feature vectors that do not require much memory during animation. But we also benefit from the advantages of the classical approach that yields realistic dynamics of synthesized words, because we use the captured data of real humans to generate these animations. Thank you for your attention.
Thank you for attending our research presentation. First, let me introduce myself. My name is Zhou, and I'm a PhD student at the University of East Anglia. In this work, we present our paper titled Constant Velocity Constraints for Self-Supervised Monocular Depth Estimation. This is a framework for predicting depth from monocular images using self-supervised machine learning. As we all know, 3D structure reconstruction from 2D images has many practical applications in self-driving vehicles, augmented reality, computational photography, and creative products, such as film visual effects. As a key to achieve this, depth estimation from real-world 2D images is getting popular in both academic and industrial research communities. In recent years, supervised learning using convolutional neural networks, for example, has become a popular method for solving many computer vision problems. However, supervised learning can require a significant amount of data labeled with ground truth information. When it comes to depth estimation, a task that requires pixel-wise labeled data, there is a little guarantee of ground truth data quality. Therefore, this is desirable to explore the development of self-supervised or unsupervised learning methods. Dislike traditional methods which predict depth of key points in a scene. Learning-based methods produce depth maps. Another advantage of our self-supervised approach compared with deploying expensive LiDAR sensors and stereo cameras is that our method only requires unlabeled RGB video sequences captured by common camera, which means we have many more available training sources. There are three main contributions we make in this work. First, we introduce the notion of velocity constancy for monocular depth estimation. Next, we describe an innovative training framework in which a depth CN predicts the depth from 3 consecutive frames of input. Last, our method yields state-of-the-art monocular depth estimation results on the KT benchmark. This slide shows 2 samples from training set. Images are referred to by one with a subscript T, and every sample composites 3 consecutive frames, T-1, T, and T+1. As we all know, explicitly inferring a depth map from a 2D image is an ill-posed problem. To deal with this problem, inspired by structure from motion techniques, depths of scenes and camera pose change are computed simultaneously on video sequences captured by a monocular camera. This is a new training pipeline we built upon monodepth 2. A depth CN and a post CN take a sequence of 3 consecutive video frames as input. The depth CN computes corresponding depth map, and simultaneously, the post CN outputs the rotation and translation T of the camera. These 3 outputs are used to synthesize a new view, and a photo consistency loss is computed with the input image, IT. The velocity depth constraint loss is computed over the neighboring images. To mental training of the networks, a novel supervisory signal is constructed by combining the photo consistency and depth constraints loss. This part explains how every component in this framework works and the basic concepts in these procedures. Given camera intrinsic parameters, equation 1 shows the procedure of how to project a 3D point XYZ onto a 2D image as a pixel UV, where pi is a projector operator. And given the depth information D, equation 2 shows back projecting a 2D pixel onto the corresponding point cloud, where pi-1 is back project operator. Given an assumption that pixels in different video frames that correspond to the same point must have the same intensity. So if a camera pose change is known, a pixel-wise between different frames mapping relation can be modeled. If both depth map D and the camera pose M are correct, the intensity of 2 pixels is the same. Therefore, a basic photo consistency loss item can be written as equation 3, which optimizes the intensity difference between 2 pixels on consecutive video frames. Apart from this basic photo consistency loss, which only compares pixel intensity values, an additional statistic constraint, structural similarity, has been shown to improve robustness for this task. In structural similarity definition, mu A is the mean intensity of an image A. Sigma A is its variance, and sigma AB is the intensity correlation of 2 images. The combined structural similarity and brightness loss becomes photo consistency loss, where alpha equals 0.85. Especially, we introduce the concept of constant velocity loss. We make the assumption that most video frames have been captured in a short time interval, during which the velocity of the moving camera can be considered as constant, as the right figure shown. Maintaining that assumption, in a set of consecutive video frames, the distance from the camera to any rigid object in front of the camera values linearly as written in equation 4. However, not all pixels follow our constant velocity assumption. For example, those objects disappear on one of consecutive frames. So, we introduce a new mask to constrain the depth loss to ensure we only consider the pixels of object common to all frames, as shown in equation 5, where ig is the mean luminous image and beta is a threshold value, set as 10 for 8-bit intensity values. Left finger shows the concept, and the visualization of a mask shows on the right. The masked velocity depth constraint loss function can be written, where the weighting parameter lambda is set at 0.001. Mu refers to the function that computes the mean of all metric elements. This slide shows how we construct our supervisory signal. We combine the photo consistency loss and the velocity depth constraint loss as a supervisory signal to optimize the model training. There are some of our training settings. We use the Adam as our optimizer, and we set 20 as the number of epochs. For learning rate, we set the negative force power of 10 for the first 15 epochs, and then decremented to the negative fifth power of 10 for last 5 epochs. We use images from a KT dataset with resolution 640 × 192. For data augmentation, we flipped each input image horizontally and also augmented brightness, contrast, saturation, and hue randomly. On the left of this slide, there is a demo from a KT test site, a video sequence captured by a moving camera. Besides, 2 additional examples of outputs shows in the right. This table shows our method achieved the state-of-the-art performance on KT benchmark. In this table, first 4 columns are error rate, the lower the better, and A1, A2, A3 are accuracy rate, the higher the better. Our method outperforms other state-of-the-art methods on KT benchmark, especially on accuracy metrics. When really compared with other methods, our method performs better than others, particularly in those edges, as white circles showing. Our method produces more precise shapes of instance than others, and keep the detailed semantic information. Those examples also show the capability of keeping semantic consistency with inputs through discriminative edges in white circles. In conclusion, we have presented a novel framework for monocular depth estimation and achieved state-of-the-art results on a popular benchmark. Besides, we introduced and developed an additional item as a supervisory signal to photo consistency loss. Finally, Our idea is simple to understand and implement, and introduces no additional learnable parameters. Now, this is the end of our research presentation. Thank you for your listening. If you're interested in our work or have any questions, just get in contact via the...
Hello. So welcome to the Q&A for our first paper session. We have the two first authors of the papers. So I guess I'll ask some questions to the papers in turn, and then we can come back if any more questions appear. So I'll keep an eye on the Discord chat. So please do drop some questions into there. Okay, so we'll start with the first paper, Neural Face Models for Example-Based Visual Speech Synthesis. I think we have Wolfgang here.
Yes, hi.
Hi, okay. So there is a question in the Discord chat. You've kind of already given a text answer, but maybe you could just like briefly kind of go back over that. So the question was about whether you plan to generalize visemes across languages and ethnicities.
Yeah, basically generalizing our approach over different person or ethnicities is not so hard. So basically we just need to capture more people. And because creating this neural face model is rather automatic, so this is more or less the easy part. The hard part is to annotate actually data, so annotate visual speech data. And this, of course, requires people in different languages. It's also not that you can map every viseme from one language exactly to another viseme of another language. So this is kind of more difficult.
Okay, I had a kind of follow-up question to that. So as I understand it, the pipeline in your method is for a single identity. Is there any scope using a similar kind of approach to learn a general model that could kind of generalize to new identities?
Yeah, basically, I mean, this variational autoencoder basically just learns this manifold of facial expressions. So as soon as we have more people, as soon as we have more captured people, for example, like you could try doing some like the stereo losses that kind of separates the identity from the expression. So this could be one way to more integrate different identities in one model. So basically you could animate speech from in one language and just switch through different identities.
So I noticed something when you were playing some of the videos, like that there might be parts of the face that exhibit dynamics that are not necessarily correlated to the speech. So the obvious one was blinking. So yeah. Blinking is kind of random or periodic, but doesn't need to relate to the visemes. I guess that's a problem when you're using an example-based approach.
Yes. So in the worst case, it could happen that you have two samples that just blinking too often or blinking not at all. So, but I think blinking is, I could say that the animation of blinking is rather simple. So maybe you can also find another way of animating the eye region or animating blinks. Like I wrote in the paper, basically we're only animating the face region. So we have separated different parts. So basically we can also control them differently. So this would be one way to solve this problem.
Okay, and something I didn't quite pick up was, do you use the discriminator or what is it that makes the transitions realistic?
The transitions are, so the discriminator in the variational autoencoder is more or less responsible to ensure that the reconstructed textures are more sharp, have more details, so that they don't stand up from the rest of the model. Like when you have a high resolution texture and then the mouth is blurry, it looks more weird. The transitions are mainly handled in this graph cut approach that basically checks how well do these animation samples match, how well do they match in a small overlapping region such that the motion is similar. So like when the ending of one VSEAM fits with this beginning of the next VSEAM, then it should have then it will have a lower error and it will be more likely to be taken. Just to make sure that the general animation is more smooth.
So would there be any scope then to have a discriminator to try to improve the realism of those transitions?
So do you mean with the discriminator, do you mean in the network training or?
Yeah, I realize that, I mean, the transitions are not handled by a network, but I'm wondering, I guess you would have to change your setup somewhat, but to try to learn or to ensure that when you're blending a transition, you don't do something that is easily detectable as not real.
Yes, I mean, basically, what you're doing with the variational autoencoder is also, I mean, basically, I'm creating a smooth manifold of facial expressions that is very likely that you have a smooth transition or realistic transition between two facial expressions. And since I'm also training with the discriminator, this discriminator would make sure that in the interpolation, there are no weird things happening. So when I'm interpolating, since I'm also interpolating between the VSEAM samples, there shouldn't happen anything strange. So basically, indirectly, the discriminator also takes care of this. Yes.
Yeah, I see. Okay, let's move on to the second paper. We'll come back if we get any further questions in Discord. So I think we have Hang here.
Yeah, hello.
Hi. Okay, so we'll start with a couple of questions from the Discord chat. So the first question is, could you detect multiple objects with different constant velocities, such as moving and overtaking cars?
Sorry, can you repeat it again?
So I think, so the question is about where you have a scene with objects or parts that are moving at different constant velocities. And I think I understand that you mask out those regions that are not constant, but the question is, could you detect and use those different objects? So if you have like a car traveling at a different speed, could you use that?
No. Our idea bases on our assumption that the time from different frames is very short, and the velocity between this time sequence is constant. So we must out the moving pixels.
Okay. So the second question is, how fast does the model run compared to the others? Maybe I could just add to that a question. Could you just clarify, is your architecture identical to, say, monodepth or the methods that you compared against? Is it just this additional loss that's giving you the performance gain?
We built our model based on the monodepth tool. So when testing, our model has the same speed with the monodepth tool. When training the model, because of the additional loss item, our model is a little bit slower than other approaches, such as monodepth tool.
Okay. Could you give any explanation? Why do you think this constant velocity loss helps with recovering thin structures well? Because it seems in your results you do a good job of getting kind of sharp reconstructions of thin structures.
I think it only works on the Kitty data set, a specific data set. Record things on the road. I think.
Okay. I have one more question. So, if I understand right, in the constant velocity loss is only based on using information in the depth maps. But it seems to me you could also use information in the relative pose. So you can enforce that, I guess, like the translation is the same between consecutive head frames. Do you do that? And if not, why not?
No, but I know someone had work on that. Use the velocity constraint on the translation metrics in the post CNN.
Okay, and so do you think that would help if you added that?
Yeah, based according to their results, it really helps the depth estimation.
Okay,
and
cool.
our research will continue on that direction.
Okay, thank you. I can't see any more questions in the Discord chat. So if there are no further questions, we will close the session here. That gives everyone about 10 minutes until the first keynote starts. So you have time to go and grab a drink or engage in some of the interactive chat in Discord. Okay, so we will end the session here. Thank you.